R-CADT is pleased to invite you to participate in the course group Applied Operations Research and Industrial Engineering. Operations research uses the scientific method to address organizational problems, focusing on providing management with a mathematical basis for decision-making. It is not a science, but more the application of science, logic, mathematics, statistics, and various theories to managerial and administrative problems. It focuses on organized systems, using interdisciplinary teams of scientists and engineers. Operational research began in 1937 in Britain and developed in countries such as Australia, Canada, France, and the United States. Smart computing, the new era of computing. Analytics is one of the pillars of the so-called smart computing. This is based on the statement of Andrew Bartels of Forrester Research, who in the study Smart Computing Drives the New Era of IT Growth, December 2009, states, "Smart computing is a new generation of hardware, software, and integrated network technologies that provide IT systems with real-time, real-world knowledge and advanced analytics to help people make smarter decisions about alternatives and actions that will optimize business processes and balance sheet results." From the above, it can be deduced that optimization based on mathematical models is a great business opportunity in first world countries and in developing countries. Franz Edelman Award for Achievement in Operations Research and Management Science. For more than 4 decades, Edelman Prize winners have been recognized for transforming the way they tackle some of the world's most complex problems. For 2022, the Edelman Prize finalists have contributed to a cumulative impact of more than $292 billion since the inception of the prize. The fundamental support of intelligent computing is the mathematical modeling of the organization, which has produced billions of dollars in profits. From the above, it can be deduced that optimization based on mathematical models is a great business opportunity in first world countries, and in developing countries. This is what is now called decision-making artificial intelligence, which is the integration of operations research with artificial intelligence. Since, in fact, operations research applications have always been artificial intelligence. Despite the economic impact of mathematical modeling projects, the commercial development of this business has been slow in non-industrialized countries, both in the creation of startups and in the use of optimization models. Structure. The group of courses aims to train the participant in the main problems that need to be solved in the planning and advanced programming of value chains specific to industrial engineering, and more generally to engineering. It is made up of 4 courses in applied operations research. Industrial supply chains. Agro-industrial supply chains. Demand chains, and transport and logistics chains. Courses can be taken all in a group or individually, depending on the student's interest. Optimization of industrial supply chains. Training in the problem of supply chain optimization, concentrating on optimizing decisions on how to optimally produce commercial products and/or byproducts offered by general industrial sector chains and the special problems posed by manufacturing industries. The following types of models are studied: designing robust and resilient supply chain, sales and operations planning, SAND-OP, inventory policy optimization, global procurement optimization, production scheduling, maintenance scheduling, scheduling of human resources to production activities, assignment of products to orders and orders to trips, available to promise, ATP, and distribution schedule. Optimization of agro-industrial supply chains. Training in the problem of agro-industrial supply chain optimization, focusing on optimizing decisions on how to optimally produce the products they offer. The course focuses on primary link optimization, farms and ranches, and its coordination with secondary link factories, value-added industries that use the animals and/or plants produced in the primary link. The following types of optimization models are studied: sowing and harvesting planning, farm network planning, feed sourcing planning and scheduling, harvesting of crops and animal cohorts, allocation of slaughtered animals to commercial products, available to promise, planning of seasons with super peaks of demand, synchronization of the primary link with the industrial link, and biomass energy generation. Demand chain optimization. Training in the problem of optimizing the demand chain for industrial products and services, focusing on the characterization of demand, mainly its elasticities, knowledge of the competition, market share, and the decision-making process in such a way that it affects the process of driving demand, with the aim of producing greater economic gains. The following types of mathematical models are studied: demand forecasting, market potential, market share projection, optimization of the marketing mix and market share, price optimization, revenue management, inventory policies, and product portfolio management. Considering the digital transformation of companies, it includes the modeling of social networks with the aim of knowing the behavior of customers and relating them to digital marketing and e-marketplaces. Transport and logistics operations chain optimization. Training in the problem of optimization of the logistics and transport chain, concentrating on the modeling of modern multimodal transport systems, trains, ships, planes. The following types of optimization models are studied: optimization of routing problems, such as TSP, travel salesman problem, and VRP, vehicle routing problem, and their continuous time modeling to produce detailed schedules. Optimization of brokerage prices in LTL, less than truck, type transport systems. Optimization of special transport systems, ships, planes, trains and truck fleets. Optimization of logistics operations in the environment of ports, airports and railways. Optimization of multimodal transport systems, and optimization of the processes of buying and selling products in international markets. In addition to courses focused on operations research for industrial engineers, which involves modeling the industry in general, RCADT offers sectoral courses that complement the knowledge required by engineers working in specialized areas. Examples of these courses are electricity and gas, oil and gas, port, mining and metallurgical, health, regional planning, and enterprise risk management. Applied operations research and industrial engineering. Aimed at professionals, engineers, mathematicians, physicists, consultants, economists, data scientists, software developers, etc., who require and/or wish to know mathematical modeling, advanced analytics algorithms, related, among others, to the implications of Industry 4.0 and its relationship with the process of evaluating the technical economic impact of the decisions that are made. This continuing education program strengthens the analytical skills and professional criteria of the participants, so that they can exercise, share and/or supervise, with propriety, the professional functions in accordance with the state-of-the-art of the methodologies and technologies that support the digital transformation of the companies. Mathematical methodologies. Mathematical methodologies correspond to the scientific foundations for implementing mathematical optimization models. Specific objectives. Training in fundamental methodologies to support modern mathematical modeling. To train so that the mathematical modeling of industrial and business processes is a generator of real socioeconomic wealth frequently used in our society. Understand that optimizing the use of resources is the scientific basis of sustainable development. Learn about systems and industrial market modeling. Learn the fundamentals of modeling real problems based on the integration between mathematical models and data models. Information technologies. Computer technologies correspond to the computer tools available, freely or commercially, to design and implement solutions to problems in social or industrial organizations. Specific objectives. Learn how to implement solutions applied in the real world by making use of the modern computer technologies available for the algebraic modeling of industrial and business systems. Present and manage live tools used by large companies to solve their optimization problems. Understand the state-of-the-art of optimization and its relationship to smart computing. Know the available technologies, as the principle of basic knowledge to be able to solve, in reasonable times, problems with millions of variable. Know the fundamentals that must be had for the assembly of models using the most effective technologies. Value chain optimization or enterprise-wide optimization. A company's value chain is made up of two chains, strongly interrelated. Demand chain determines all the processes that are carried out to attract customers in the markets, and supply chain determines all the processes that are carried out to produce the products that customers want to consume. The diagram presents the chain of the company's production chains that together make up the value chain. One of the greatest evolutions in the modeling of companies occurs in the interpretation of their value chain. The first step in business modeling arises with mathematical models of industrial processes, which are characterized by their complexity, with very little interrelation between them. In this aspect, with a very simple vision, it can be said that the mathematics of industrial processes do not change, that what is constantly changing is the power of information technologies. This is followed by ERP, Enterprise Resource Planning, which in its initial versions do not access mathematical models. ERPs evolve in two systems. SCMs, Supply Chain Management Models, aimed at optimizing the production of companies. And DCMs, Demand Chain Management Models, focused on sales and marketing management. The union of the two modeling systems produces the Sales and Operations Planning Model, S&OP. Advanced versions of S&OP are optimized in an integrated manner as a single model, and not by coordinating two models. The first option is the most effective. The Integrated Business Planning Model, IBP, includes the financial chain in the company's planning. The evolution of this paradigm of technological tools is presented in the diagram. Thanks to computational power, the integration process has continued to grow. The diagram presents the original S&OP model, and the current version, which integrates more and more models. There are multiple points of view to analyze the planning and programming of production chains. The second aspect is the hierarchy of decisions, that is, their coverage over time, according to their impact and the characteristics of the models to be used. The first two levels are strategy and tactics, which fundamentally analyze the long and medium-term impact. At the bottom of the hierarchy is programming and advanced real-time control. Today, thanks to IoT, a new application has been created that is real-time tactical planning, which did not exist before. This involves adjusting the tactical planning of the chains as impact events occur in the medium term. Another point of view is the regional one, which is necessary in global production chains, which must be coordinated in space and in the global transactions they carry out. State of the art in 2021. Robots, algorithms, can autonomously and automatically perform specific processes with pre-established coordination, limited intelligence, and little interaction between robots. The robotization of powerful processes in real time, supply chain planning, operation of production plants, optimization of traffic systems, coordination of marketing campaigns, etc., is relatively unwidespread. Today's computing power based on the unlimited availability of processors offers electronic computing capabilities at a completely different level than in the past. Industry 4.0. Robots capable of autonomously carrying out high-coverage processes based on intelligent interconnection, mathematical conversation, between robots using information from big data systems, based on IoT. The current state of technology can be synthesized at the confluence of computer parallelism and complex mathematical modeling. Only companies that fully understand and manage the interrelationship between these pillars of socio-economic development will be able to fully participate in the generation of knowledge required by Industry 4.0. Enterprises can't take advantage of the availability of hundreds of thousands of processors if their analytical tools can only organize high-level mathematical calculations around the monolithic concept of a single processor. This evolution has led to modeling based on artificial hypothalamus, supported by the integration of mathematical programming and artificial intelligence. Artificial hypothalamus. Artificial entrepreneurial brains rely on the development of parallel thinking, when a complex system must be analyzed. And reality is complex. The diagram presents the simultaneous evolution of three fundamental aspects in Industry 4.0: information technologies, analytics, and mathematics. Jesus Velasquez Bermudez, who is the creator of the artificial hypothalamus, the result of the integration of mathematical programming with artificial intelligence based on neuroscience. Most of the things and processes that humans use have been totally affected by technology, which has opened up to the human imagination producing previously unsuspected results. Mathematical modeling should not escape this process, starting from discovering the mathematical foundations that serve to establish the laws that govern physical, industrial, economic, biological, health, and social laws, and with them build mathematical models, and increasingly powerful calculation algorithms. Later, Velasquez Bermudez expanded his work to create the artificial brains. Nowadays all knowledge and technology are available to develop a higher-level artificial intelligence, which emulates human intelligence in any type of human organization, and can be called the artificial hypothalamus of the organization. The power of today's technology is not in the mathematical calculations it allows to be performed, it is in the mathematical calculations we can imagine we can perform. Jesus Velasquez Bermudez in 1990 created Optex, Optimization Expert System, an optimization platform that was developed with a new vision of mathematical programming. To date, Optex has completed 34 years of continuous growth and updating. Proof of this is the current R+D plan that HI is developing to incorporate the latest achievements of AI, such as ChatGPT, to facilitate the dissemination of mathematical modeling in Industry 4.0, taking it to the level of people not specialized in the subject. You can find more information about Optex in the LinkedIn post. From simplex method to mathematics-based artificial general intelligence. Hierarchical coordination of planning tools. It is traditional to organize decisions hierarchically into strategic, tactical, and operational. The operational decisions are divided into the scheduling and advanced optimal control. However, due to the technological progress generated by Industry 4.0, mainly in relation to smart metering systems, nowadays we can talk about a new type of online optimization modeling, real-time distributed optimization. From the point of view of mathematical modeling, hierarchical levels are intertwined and coordinated through the boundary conditions in time, and common modeling that can be shared. The modeling strategy of HI is that all models of a decision support system can communicate with each other. Large-scale optimization and artificial brains. One of the fundamental ideas of the artificial brain is the atomization of the system, bottom-up approach, to integrate multiple mathematical models, using the framework of large-scale optimization methodologies, like multi-level Bender's theory, and Lagrangian relaxation. The same system can be organized hierarchically from multiple points of view. Because they are the same system, all these views must be equivalent. That is, in a non-degenerate optimization model, they have the same solution. The image presents the hierarchy from the point of view of regionalization. Considering the vision of large-scale optimization, which can have multiple points of view, HI developed the multi-Bender's decomposition, MBD, algorithm, to emulate the coordination of multiple points of view, just as the human brain does, following the studies carried out by Jeff Hawkins, summarized in his book, 1,000 Brains. On the other hand, if other intelligent structures are studied, different from the human brain, it can be concluded that this structure is not necessarily the best, and that there are alternatives in nature that can be artificially implemented. An example is the octopus, which has 9 brains, 3 hearts, and 2 memory systems, which it uses to control each of its 8 limbs independently, allowing it to move nimbly and react quickly to any threat. In addition, it has a central brain that hierarchically coordinates the secondary brains. This is one case, among several, of beings with multiple brains. It is evident that the structure of cephalopods is reproduced in human organizations, so a multi-brain artificial brain can be useful. On the other hand, if other intelligent structures are studied, different from the human brain, it can be concluded that this structure is not necessarily the best, and that there are alternatives in nature that can be artificially implemented. An example is the octopus, which has 9 brains, 3 hearts, and 2 memory systems, which it uses to control each of its 8 limbs independently, allowing it to move nimbly and react quickly to any threat. In addition, it has a central brain that hierarchically coordinates the secondary brains. This is one case, among several, of beings with multiple brains. It is evident that the structure of cephalopods is reproduced in human organizations, so a multi-brain artificial brain can be useful. In the global nature of modern companies, which must fulfill planning functions at different levels of their regional distribution for industrial, financial, and commercial operations, a multi-brain artificial brain structure is useful, as in cephalopods. This hierarchical vision of the system can be converted into a different, but equivalent, approach. A vision focused on the mathematical neurons, which form a network connected according to the map established in an artificial cerebral cortex, forming what would be an artificial hypothalamus, which feeds its decisions from an artificial hippocampus, which stores the history of the system, in terms of math models, and executions of these models. Like the human brain, the artificial brain is made up of the following artificial components. Neocortex acts as an organizer of the connectivity of mathematical artificial neurons. Hypothalamus, it is the central processor that coordinates all the models included in an artificial brain, and hippocampus, it is the memory of the brain that stores the history of what is happening in terms of mathematical model runs. It is coordinated by a traditional artificial net. The most important planning function in a company may be integrated business planning, IBP, which integrates, at least, three areas: finance, marketing, and sales, and production. The IBP model can be looked at from 3 points of view. 3 independent models, which are integrated through a process in which the input of one model is the output of another. A monolithic model that integrates the 3 models, and that is run periodically, and an artificial hypothalamus that acts autonomously, in a distributed way, in real time. Oil and gas enterprise-wide optimization system integrates mathematical models for each of oil and gas's supply chain links, so that supply chain planning is managed with a holistic view. At the level of industrial facilities, the oil and gas chain involves connection between industrial facilities, using multimodal transport systems. Based on the models to be integrated, and considering the magnitude, and the association between them, it is considered that the hypothalamus of a refinery business should be made up of 5 subsystems. Oil refining and petrochemical. Refinery industrial services. Water treatment. Multimode transport, and financial and fiscal. Now, if you look at each business from the point of view of functionalities, you have an artificial brain made up of multiple models, associated with the problems of the administrative functions of each industrial plant. It generates another brain of the same problem. Artificial brains can share models such as production, where the sales and operation planning model belongs to the brain of systems and the brain of functions. In the same way, the models can share math problems, and the problems can share equations. Construction of artificial brains. The methodology for building an artificial brain follows a formal modular process, which High calls structured mathematical modeling. First, all mathematical equations, and their components, are stored in a relational database, part of an artificial hippocampus, which can be handled using SQL, standard query language. This implies an open and standardized structure, which is not common in mathematical modeling. Sets of constraints form problems, called by High, mathematical artificial neurons, and sets of problems form models, and a set of models forms an artificial hypothalamus, which is linked to the corresponding artificial cortex, a network of mathematical artificial neurons, and the artificial hippocampus, memory, which stores, in addition to mathematical formulations, the history of all model runs. From the concept of enterprise optimization, it evolved towards enterprise-wide optimization, which implies expanding the coverage of the decision support system, which High calls enterprise-wide optimization systems. Visually, it is easy to see the evolution of the IBP concept to AWO, which covers all operational functions of an industrial organization. This leads us to 2 problems that must be solved from a computational point of view. If traditional approaches are used, many programmers are required to generate all the source code needed to develop and coordinate all models, and It takes a lot of computational power to solve the built-in problem. In order to solve this situation, HI has developed OptX, Optimization Expert System. A generative artificial intelligence, which is responsible for producing all the source code required by an artificial brain, using large-scale optimization methodologies to solve complex high-dimensional problems. The diagram presents an artificial hypothalamus of an IBP process. Finally, decision-making artificial intelligence is a new term, coined by HI to refer to optimization algorithms aimed at decision-making. It could be said that its birth coincides with the launch of the ENIAC computer, in 1947, which gives voice to digital iterative algorithms such as the simplex method, created by Danzig. It is very little known, and there are very few companies specialized in this area of knowledge. HI is one of them. HI has accumulated 50 years of intellectual property in this field. The course group director is the founder and executive director of RCADT. Engineer Velasquez Bermudez's experience in applied operations research dates back to 1972, which means that he has accumulated 50 years solving real-world problems doing engineering consulting using mathematical models. R-CADT is the most applied academic center in the integration of the teaching of mathematical programming and artificial intelligence. For more information you can consult the URL. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.